Bismillahirrahmanirrahim. I welcome you to CSC 339, Data Communications and Computer Networks. Today we'll talk about the application layer first. The application layer will be covering the different applications that are network applications that are there that we use in daily life, and the protocols that are required by these applications. So network application, you can say, is the basic reason behind computer networks. So imagine if we could not receive any useful application, there would not be any need for the networking protocols that support these applications, or there would not be any need of networks. So the basic reasons that we use networks today, in homes, school, governments, businesses, that is because the applications have made the internet as an integral part of our daily activities. So the basic driving force behind computer networks is a network application. So every day we are coming up with exciting applications that demands more and more innovation in computer networks. And in fact, historically, we can establish, we can have a timeline to discuss different internet applications. For example, if we talk about the era of 1970s and 1980s, so these includes these two era includes classic text-based applications, such as text mail, remote access to computer, or file transfers, or news groups. So in this era, in 1970s and 1980s, so we have classic text-based applications. Right? And these includes what, as I mentioned earlier, text email, remote access, and of course, yes, file transfer. And news groups. And if we move on, and if we talk about mid-1990s, so we have the killer internet application. So we have the killer internet application, right? And what it is? Yes, you're right. World Wide Web, WWW, right? World Wide Web. Right. So obviously, this includes what? This includes when I say World Wide Web. So I mean to talk about web surfing. What else? Search, yes. And most importantly, electronic commerce, right? Where we are generating a lot of business these days. electronic commerce. Okay, and uh, since uh, since 2020, we have an explosion of popular voice and video applications. We have explosion of voice and video applications, such as voice over IP, voice over IP, uh, yes, video conferencing, um, video conferencing maybe over IP. And the example of it is Skype. Skype. Then, we have user-generated video distribution, right? Such as YouTube, where you are creating the content and distributing it, right? And then we have movies on demand, such as Netflix and many other, similar applications, right? And recently, we are, what's happening now? We have seen the emergence of new generation of social networking applications. So we have uh, new generation of uh, of social networking applications, such as Facebook, uh, Twitter, right? And you know what? These applications have created engaging human networks on top of the internet's network of routers and communication links, right? Making it more, interesting and involving as far as human interaction is concerned. Right. So this means the reason for discussing all these applications and dividing it in a timeline is to understand that the basic, driving force behind computer networks is network applications, right? So we have to understand what sort of different network applications are there. Obviously, we cannot, discuss all the network applications here. So what we'll do is we'll discuss some of the very important and key network applications, some of the applications uh, that we use in daily life, such as web, DNS, email, uh, proxy servers, and then we talk about some of the peer-to-peer applications in this and coming lectures, couple of coming lectures. So let's start talking about the principles of network applications. Okay. So my screen is visible.
Yes, sir.
Thank you. So some of the network applications, obviously, it's not possible for us to cover all the applications, right? So some of the network application out of this huge list that we'll be covering involves, email. Obviously, I'll be talking about. Uh, I'll be talking about email, we'll be discussing web, we'll be talking about peer-to-peer file sharing applications, and apart from that, we'll be talking about DNS and some other important file transfer, most importantly, right? Applications, right? So before we move on and start discussing the different applications, it's important for us to look at the principles of networking or network applications. So when you want to create a network application, you will write your code in C, Java, or Python. Some part of the code will run on one machine, or say a client or a host, and the other part of the code will run on the other machine. So usually, when we develop a network application, right, it will develop on either a host, a part of it will run on the host, and a part of it will be deployed on the server, right? So it runs on the end systems. The most important thing is the network application system runs on the end systems. Why? Because these core network devices, they're only responsible for forwarding data to the specific end machines. These core network devices do not run user applications, right? So we need not to write softwares for network core devices, okay? Because the functionality of core devices is to forward the data, right? An application is supposed to run on end machines. So whatever code we are writing, a part of it will run on one machine, which is the host, and the part of it will run on the other end, which is maybe another host or a server, depending upon what different sort of network architecture our application has, right? So if we talk about web server softwares, for example, to take an example, so a browser part is there on the host here on our laptop or maybe our computer, right? And then we have the site or the server containing the web objects that we would like to access, right? So the network application, the principle is the network applications always, run at the ends, okay? And we do not involve the core network devices, core routers, and other devices, network devising to run the network application software, right? So this obviously simplifies and our design and is in link with the TCP/IP design philosophy, where we said that the application will run on at the ends. Okay. So whenever we have to communicate, obviously the host machine will interact with the server or maybe the other host in order to perform a specific functionality. So network applications have two architecture types. There are two possible structures possible for the network applications. So either we have this client-server application or we have this peer-to-peer application. So when I say client-server application, this means there is always a host that is always on, and we call it a server that provides services. Right? For example, a web server provides web services all the time and is listening for the incoming connection, and the host machine or the client can connect to the web server or to the server to get the data. And on the other hand, we have this peer-to-peer application where there is no defined division of machines into client and server. In fact, these are machines at the same level, and these machines are providing services to each other. So we call it what? Peer-to-peer architecture. And there is also a hybrid, architecture where there is a server only for the reference of the host machines or the peers that we want to connect together. So let's talk about client-server architecture first. So in this client-server architecture, so some part of the network application is running on the server, right? And some part the network application is running on the client machine. So server is a machine or a host that is always on, right? So server is always on, right? So it's important that server or this host is always on. And since it's always on and it's expecting incoming connections, so it has a permanent IP address, that does not change and is always there. But the problem is that maybe uh, you know a social networking site or a search engine um, you know uh, can quickly overwhelmed if it has not, if it has only one server handling all the requests. Imagine Google receiving thousands and thousands of requests. So do we have one server for Google? Is it enough having single server for a very popular website where we are
No,
receiving? No, it's not. So this means um, we need to have more servers, and we need to scale the system up, right? By introducing more servers so that we can handle more requests, right? So that's why we have this concept of data center here, right? So data center, what it does is it houses a large number of servers, right? So data center is housing a large number of hosts. Why? To create a powerful virtual server, right? For example, if you talk about the most popular search engines like Google and Bing, or you talk about internet commerce like Amazon, eBay, or maybe you talk about the web-based email like Gmail and Yahoo, mail, or you talk about the social networking platforms such as Facebook and Twitter, right? What do you think? Do they have a single server, or let's talk about data center? Do they have one data center? You know what? Only Google has 30 to 50 data centers distributed around the world. So if I only take example of Google here, so it has how many data centers? It has 30 to 50. I'm not talking about single server. I'm talking about data centers. Okay, and these data centers are distributed around the world. Why? To collectively handle search, YouTube, Gmail, and other services, right? So because a data center can have hundreds and thousands of servers, and which has which must be powered and maintained, right? So this means these client server application where the client communicates with the server, right? And maybe client can come and go, can connect anytime, but
mhm.
server is there up and running, and it can receive thousands and thousands of requests, right? So these systems are not scalable, self-scalable, right? Are you getting my point? So this means if the number of users are increasing, if the number of users on YouTube, Facebook, and Twitter are increasing, they need to increase their capacity. Data centers having more and more servers, virtual servers, right, where they can handle the incoming requests from the different ever increasing number of clients. Okay, so scalability is an issue with this sort of network applications where we have a host that is always on, that we call it a server, and it provides services. It can provide different services, as I mentioned earlier, such as search engines, internet commerce, web-based emails, social networking, and whatnot, right? And in order to make it scalable, depending upon the expansion of the number of requests that are coming in, we need to move to data center, and we need to have number of data centers distributed across the world to handle the search and different types of services for which the requests are coming in. So this is one possible, architecture of network application. Okay, and the second type of architecture that an application can have, or we can develop a network application having this specific architecture, is known as peer-to-peer architecture, where the peers are directly communicating with each other. Okay, so there's no always on server, right? So there are certain arbitrary ends where the machines will directly, communicate with each other. For example, a peer, you can see this peer is directly communicating with this peer, right? So peers request services from each other or from the other peers and provide services to, the other peers in return. So peers are the devices at the same level, right? So maybe the server is there in a hybrid architecture, but this server is just to maintain um, the information of the peer, the reference of the peer. So if this machine wants to communicate with this peer, it will first, contact the server, will get the detail of the peer, and then the data transfer between these two peers will be happening directly, right? In the transfer of the data, the involvement of the server is not there, right? So if we talk about the most popular and traffic-intensive applications, and so these are based on peer-to-peer, architectures. So these applications include what? These applications include file sharing, applications such as BitTorrent. You might have used it, and we'll cover this in detail at the application layer. It's a trading algorithm and other details. So it involves BitTorrent, and then peer-assisted download applications such as Yonley. Then we have internet telephony such as Skype, which is also peer-to-peer. What else? We have IPTV, right? So this IPTV is also, a peer-to-peer uh, application, category. An example of such an applications are um, Khan and TP Stream. Right. So these are some of the applications that involve this, peer-to-peer application. Obviously, out of all these applications, we'll talk about the very famous, file sharing application, BitTorrent. Right. Um, you know, these peer-to-peer applications are self-scalable. So remember, we identified the problem with client-server architecture-based application, that it has a scalability issue, and then if there are more number of requests are coming in, the user has increased. So this means we have to introduce more virtual servers, more data centers, right? But if we talk about this peer-to-peer architecture, so this peer-to-peer architecture is, is self-scalable. How? And we'll discuss this in detail, and we'll also have a comparison later on about the peer-to-peer application and client-server application scalability and effectiveness when we talk about the BitTorrent application. But for now, if we add more number of peers here, what will happen? What do we think? Will it increase the load on the network in terms of any particular machine? No. Adding more peers means there are more machines that can provide services to the other machines in the network, right? So this means uh, you know the peer-to-peer applications are self-scalable, right? So this is very important. These peer-to-peer applications are self-scalable, means new peers bring new service capacity. Yes, of course, as well as new service demands, but the new service capacity is the important thing there. These new peers will also be providing, the services as well. Okay, and so we do not need to add more and more, data centers, and we don't no need to invest into the virtual servers and all that, right? And remember, these peer-to-peer applications are, uh, you know, uh, are ISP friendly. So it's ISP friendly. That is, sorry. So most residential, ISPs, including the ones that are providing DSL services or maybe the cable ISPs, have dimensioned for asymmetric bandwidth usage. Asymmetric bandwidth usage mean that there is a different bandwidth for uploading the data and for downloading the data. That is, आवाज आ रही है आपको?
Yes, sir.
Okay, that is for downstream. The more bandwidth is for the downstream than the upstream traffic, right? But if you talk about the peer-to-peer, for example, video streaming and file distribution applications, these shift upstream traffic from server to the residential ISPs. Thereby, this means putting significant stress um, uh, on the from the servers to the ISPs. So future peer-to-peer applications need to be designed, for example, that are more um, that are more ISP friendly, right? Why? I will like to elaborate this point. So when I say ISP friendly, what do I mean by this? I mean, um, for example, this machine A is connected with this, ISP. Let me assume there is PTCL, okay? And we have asymmetric bandwidth. When I say asymmetric bandwidth, this means there is a different bandwidth for uploading. So this is this traffic is upstream, where I'm sending data or request to PTCL, okay? And this is the downstream, where I'm getting data from PTCL. Okay, about summation. So at the moment, for example, we are using DSL at our homes. So it's ADSL, asymmetric digital subscriber line, where there is more bandwidth for downloading the data rather than uploading the data. Okay, for example, just give me an example. For example, if we have 4 megabits per second Ethernet DSL connection, so maybe 1.5 megabits per second, just assuming, is for downloading, and only say 500 kilobits per second is for uploading. Okay. Why? Because most of the time, what we are doing, we are downloading the data. Yes, no?
Yes, sir.
Yes. So we need more bandwidth for, downloading the traffic, right? So what the peer-to-peer applications have done here? What do you think? Now, if you're using this BitTorrent, you're also doing what? There is another, for example, device here B. You're also sending file chunks. Yes, no.
Yes,
Yes,
sir.
sir.
You're shifting. Yes, yes. So file distribution application work just like BitTorrent. What it does is you know it shifts the upstream traffic from servers to the residential ISPs. Now there is no server here involved, so there is no server here that is forwarding data to machine B now. Now what is happening? Machine A has file chunks, or maybe there are many other machines here that are sending these chunks to machine B through this ISP here. So where all of the where all of the load is. Where do we have the load now? On the server or the ISP?
ISP पे sir.
ISP, right? So this means the number one requirement from the peer-to-peer application is that it needs to be ISP friendly, right? The future peer-to-peer applications need to be designed in such a way that these are ISP friendly. Why? Because most of the ISPs have this, arrangement where most of the bandwidth is being used for downloading the data, and a fraction of the bandwidth is being used for uploading the data. Right. The second requirement from the peer-to-peer application is security. Um, because the peer-to-peer applications are highly distributed, and they're obviously open in nature, so it's more challenging to secure peer-to-peer application. So the data is coming from the many different peers. These peers are trusted. We have no prior interaction maybe with these peers, and it's highly distributed. There is no center point where we can trace and we can track an attack from. So we need to come up with network applications um, that are more secure, right? At the moment, this is an issue with the peer-to-peer applications. Obviously, we'll talk about it when we'll discuss BitTorrent as well, right? And then the number three, if we want to, um, ensure its successful, future of the peer-to-peer applications, we need to give incentives. Incentives, right? So the success of future peer-to-peer applications depends upon that we convince the user to say volunteer bandwidth, storage, and uh, computation resources to the application. This point is very important, right? So future application may demand that this host will volunteer to do some sort of what? Computation, okay? Or maybe will temporarily store my data or any other peer's data, or will volunteer the bandwidth, okay? So why this machine should do all these things? Why? What do you think? Is there any incentive there at the moment? What do you think? Do we have any incentive? No. So if I want this peer-to-peer application to be, adopted, at a large scale, or I want it to be successful, we want it to be successful, so we have to come up with, some incentives, right? So all these, challenges are related of an incentive design, right? So we need to see how we can give incentive to this host, right? This host, in terms of it can be a monetary incentive, it can be any other form of the incentive, so that more and more machines are volunteer or are ready to share the computation, storage, and bandwidth resources. Let me give you an example. It happens that when you're using this BitTorrent peer-to-peer application, so you tend to download something, but you're not willing to upload, the file chunks. Yes, no?
Yes, sir.
So, so most of the time we reduce the upstream, bandwidth or upload data rate. And it's important to know that it will not affect our download rate, right? So if we give some sort of incentive, more and more individual applications or the host machines will, start using this peer-to-peer or peer-to-peer applications will become more popular, right? So these are some of the requirements from the you can say these three are some of the requirements from the future peer-to-peer application architecture or design, where we want it to be ISP friendly, we want it to be more secure, we want it to have some sort of design involving incentives to make it more popular among the users. Okay. So before I move and talk about the application layer protocols and that an application has to make use of, I would like to talk about. I'll take a minute to talk about uh, the process, right? How a machine is able to communicate with the other machine implementing a network application. Okay, and okay, let me see. So we have to switch back for a while. I'll switch it off, and we have to move to our OneNote. समझ आ रही है?
Yes, sir.
समझ आ रही है? अभी वैसे हमने कोई एप्लीकेशन डिस्कस नहीं हुई, तो मैं सिर्फ हम आप देख रहे हैं कि ये क्या है, इसका आर्किटेक्चर्स क्या है, फंडामेंटल्स क्या है. Okay. Is my screen visible now?
Yes, sir.
Okay.
Yes, sir.
So, okay, thank you. So, when I say that a machine, or let me call it a host, communicates with a server, so what happens here is that we have a, on both ends we have a process, right? So we have a process here on host A or host machine. So we have a process. We also have a process here on the server, and this process is controlled by application developer. So this process is controlled by application developer. And similarly, on the server side, we also have a part of the application process, a part of the application running, and we have a process for that, and it is also controlled by application developer. Okay, and then we have here on both the host and the server, we have TCP, or we can also have UDP at the transport layer also. So we have TCP there as well, and we have this, TCP. And when I say TCP, I mean TCP with buffers and variables, right? all the buffers and the variables that we have to maintain. So we will also have TCP with buffers and variables. Right. And using this TCP connection, or maybe UDP, the host will be sending or receiving data from the server. And yes, this defines our internet. Okay, so it's a sort of cloud where we have a lot of data. And remember, this TCP with buffers and variable, this is controlled by operating system. This is controlled by operating system. Look, the same is the case on the server side. It is controlled by operating system. Right. And now the question is how a process that is controlled by application layer or application developer at the application layer communicates with the TCP with all their buffers and implementation that is controlled uh, by the operating system. Since this process sends and receives messages, send messages into and receive messages from the network through something, right? So here, what do we have here is we have, in between these, we have, socket. Okay. So this process sends or receives messages through this door between the process and the transport layer. And we call it what? We call it a socket. So similarly, the server sends or receives messages to the network from the network using this socket, right? So this socket is a sort of a door or an opening, right? And we also call it what can call it application programming interface, or we call it API, right? Application programming interface. And yes, we are familiar with this. We call it what? We call it API, right? So this API between the application and the network, since the socket is, is the programming interface with which the network applications are built. Okay. So for example, if you are a application developer, it only has control on the transport layer side. How? And in what terms? It has the only the control that is with you is the choice of the transport layer protocol, right? Or maybe probably what you can do is you can fix some of the variables. That's it. The rest of the control is with the operating system. Let me write it here. So being an application developer, what I can control here? Number one, being an application developer, I can only select the transport protocol. So I have a choice of transport protocol. Okay. Or the second choice is probably, or perhaps I have the ability, or I have a choice to fix a few transport layer parameters. So what else the application developer has access to? It has access to transport layer parameters. Parameters such as, क्या ख्याल आप लोगों का? Parameters uh, such as maximum buffer and maximum segment size. Rest of the implementation is with the operating system, right? So we have to access it through an interface that we call application programming interface. And how we can address this process, how we can address the other machine, and we have covered it earlier as well. For that we have to uh, in order to define this socket, I have to provide both IP and port number. Remember? Right? At the moment, I'm talking about the UDP socket, and for TCP socket, I have to have 4 tuples, and where this port number is the process address, right? And this IP is the IP address of the server machine. Right? Am I clear?
सर ये पॉइंट 1 और 2 बता दें दोबारा, ये आपने क्या बताया था इसमें?
No worries. So मैंने ये कहा कि if we talk about the control of application developer on the network layer services, so at max it can do 2 things. Number 1, I have a choice to select the transport layer protocol. Either it's TCP, it's UDP, right, or it's RTP or any other variant of TCP. Okay. Number 1. And the number 2, what I can do is I can select the maximum buffer size, or I can select the maximum segment size. So these are the only choices or the controls that are available with the developer of an application. The rest of the implementation is with the operating system. Okay.
सर मैक्सिमम बफर साइज और कौन सा?
Maximum segment size.
Okay, sir.
Right. So when we talk about a network application make use of different application layer protocols. When I say protocol, we know that the protocol is a set of rules and regulations. And when I talk about the network layer or application layer protocol, this means what type of messages will be exchanging. And that we'll see when we're discussing different network applications. I mean, what will be the request and what will be the precise response? What is the syntax of the message? What is the semantic meaning here? Right? And when and how the processes will send and respond to certain messages, and in what sequence, right? So these are called, these basically defines what? These defines the protocols, right? So these defines what? These things define what? Protocol. And now certain protocols are open. I mean, they are available. Their RFCs are available. For example, if this HTTP is there, so we have, we have 2 RFCs: request for comments. Request for comments is a technical document that has all the implementation details, right? For HTTP, we have 2 RFCs: RFC 1945, and then we have RFC 2616, right? So these 2 RFCs combinedly gives the details about the implementation of hypertext transfer protocol. So if you want to develop an application using HTTP, so you have to, where there is a server and there is a client machine, so you have to look for the details in request for comments 1945 and 2616. But some protocols are proprietary. For example, we don't have open RFCs or open protocol for Skype, because Skype is a proprietary protocol developed by a company, is not publicly available, right? So their details are not available to us. Okay, So before we talk about a specific application, let's talk about what sort of transport services available to network applications. Okay, so there are different sort of transport layer services that an application at the application layer makes use of, right? So we have number one, we have data integrity. Data integrity means whatever data we are sending, is is being received on the other side, right? Okay, means these the applications that require data integrity are loss intolerant. We cannot accept a loss here. For example, if you're transferring a file or you're downloading something from the web or you're having a web transaction, we need 100% data integrity or data reliability. When I say data reliability, this means it guarantees data delivery service. I mean, the data will be delivered to the other side. And if some part of the data is not available, this will affect the whole process, right? So the applications such as file transfer or web applications, these are the applications where I need data integrity, right? And maybe there are applications such as audio that are loss tolerant. Loss tolerant application means where the losses are acceptable, right? For example, if you're using an audio application, there might be a loss, and that loss is acceptable because it will only create a small glitch in audio video, and it's not a crucial impairment, or it will not affect the application. But if there is a loss in the file transfer, it will not be able will not be able to recover the whole file, right? So we may have to retransfer the file again, right? So the first sort of service that a transport layer can provide to the application layer is data integrity. Okay, and then we have the timing. So timing means what? Uh, that a transport layer protocol can provide timing guarantees, right? For example, uh, we will get a response and no more than 100 milliseconds, right? And such a service would be very helpful or appealing to the interactive real-time applications such as internet telephony, virtual environments, teleconferencing, multiplayer games, right? Why? Because all of these applications have tight timing constraints on the data delivery in order to be effective, right? So this means these are the applications where we need what? Where we need low delay in order to be more effective, right? So we can have, by the way, it's very hard to provide timing and throughput, guarantees. It's very challenging, right? So if we talk about the throughput, there are some applications that are bandwidth sensitive, right? There are applications that are bandwidth sensitive. Okay, means what? Means they require a minimum amount of throughput to be effective, right? But on the other side, maybe we have applications that are, elastic. These are the applications that make use of whatever throughput they get. Okay, I mean they can make use of as much or as little throughput as happens to be available. Examples of such an applications, I'm talking about this elastic application, electronic email, file transfer, web transfer. These are elastic applications. Of course, the more throughput is, the better, right? Okay. And then obviously the security. The transport layer can also provide security to the network applications, implementing, SSL and other techniques that we'll cover later in the course, right? So we can provide data integrity, end-to-end authentications, right? So these topics will be covered in the later stages. So we can summarize it, this discussion from this table. So we have variety of different applications. We have, we'll see one by one, we'll discuss one by one. So we have this, file transfer application. What do you think? A file transfer application is loss tolerant? No. So no losses are acceptable, right? So data integrity is important, is required. Are these applications elastic? Yes. Right? So if you're transferring a file, if you have more bandwidth available, good enough, right? Even if less data rate is available, so it will still serve the purpose and will be able to download a file. Is it time sensitive? No. These applications by nature are not time sensitive. These are all real-time multimedia, online games, right? Or these applications are not similar to other, real-time interactive applications, right? Like internet telephony or teleconferencing, et cetera, right? So are you clear about the first application here, file transfer? आवाज आ रही है आपको?
Yes, sir.
आपको समझ आ रही है, right? And then let's talk about the second application that we make use of in daily life, right? Email. What do you think? Are losses acceptable in email? Somebody sending you an email and there is no attachment.
No, sir.
No. Is it elastic in nature? Yes. That's fine if our bandwidth is available, good enough, right? If not, it will still serve the purpose. Is it time sensitive? No. And what about this, web document? No losses are acceptable. Yes, it's elastic, right? And it's not time sensitive. What about this real-time audio video? Is it loss tolerant? Yes.
Yes, sir.
Is it, in terms of throughput, do we require a specific minimum bandwidth? Yes. Is it time sensitive? Yes. A response or a delivery under 100 milliseconds is desirable, for example. What about this stored audio video? Is it loss tolerant? Yes. And we have the same parameter as. And what about the interactive games? Losses are okay, right? We need few kilobits per second and up the data rate. And time sensitive, but these applications are time sensitive, yes. What about the text messages? Are losses acceptable? No. Is it elastic? Yes. Okay, all right. So, and for this purpose, looking at the type of application and the requirement, we have two types of protocols at the transport layer. We have what protocol known as TCP that provide TCP services, and then we have user datagram services. TCP is reliable transport protocol, right? It's reliable because there are no losses here. And for that, we have implemented certain flow control mechanisms, certain congestion control, where we can throttle the sender when the network overload. And remember, the TCP server service does not, this is important here, does not provide timing, minimum throughput guarantees, and security. It's challenging, I mentioned earlier, right? And it's correction oriented. A part of this discussion has already been covered in our in the previous slide or in the previous lectures, right? And what about the UDP service? Is unreliable data transfer. It does not provide reliability, flow control, congestion control, timing, throughput guarantees, or there is no connection setup is required. And there's an obvious question here. Why bother? What do you think? Why do we need UDP? Are there any applications that you think that would be using UDP? क्या ख्याल है आप लोगों का? कोई ऐसी एप्लीकेशंस होंगी जो आप समझते हैं कि यूडीपी इस्तेमाल करेंगे पे, जबकि टीसीपी इतना अच्छा है, उसमें रिलायबिलिटी है, right? Data integrity is there. We have flow control, so that we should not overwhelm the receiver. We can also control the congestion of the network, right? So then, why do we need UDP?
Broadcasting.
What else? Broadcasting, in a sense. It has nothing to do with broadcasting, by the way. So it's a speed is there, right? So there are applications that demand speed, right? आइए इसको एक और perspective से देखते हैं. So now look at the application. The application is email. What was the requirement of email? No loss. Plastic. There's no time sensitivity, right? So what do you think? What sort of transport layer protocol is required? TCP. Why? Email queue TCP. Yeah, because here we have what? Where we have the requirement of here we have the requirement of reliable data transfer. Yes, no?
Yes, sir.
Yes, so that's why we have TCP here. And what about the remote, or let me talk about this web. It's again, the reliable data transfer is a requirement, and that's why we have the web-based applications make use of TCP at the transport layer. What about the file transfer? Again, the reliable data transfer is a requirement. And for that matter, we have what? We have TCP at the transport layer. And what about the internet telephony? Right, so the primary choice is for the is to go with the UDP, but as a backup, they also implement TCP as well, right? Okay.
Yes.
So you might be wondering why TCP is here. Okay. You might be thinking why TCP is there, right? So as a backup, they have also implemented the TCP, right? But the primary consideration is to go with the UDP. Why? Because it provides speed. Timing is important here. Same is the case here. So that's why here we'll go with the TCP. So see, so whatever application we develop at the application layer, either at the transport layer, we'll be using what? We'll be using TCP or we'll be making use of UDP. And if I want to implement an email application, I'll be implementing what? An application layer protocol known as SMTP. Simple Mail Transfer Protocol, and its details are given in request for comments 2821. Similarly, if I want to implement an application, I need to implement what? Hypertext Transfer Protocol. And as I mentioned earlier, its details are given in RFC 2616, and there's another RFC which is not listed here, 1945. Okay, and if I talk about Skype, its RFC is not there. Why? Because as we discussed earlier, it's proprietary. Okay, so in the next class, we'll talk about we'll start discussing the web and HTTP application first, and we'll see how you know web-based applications work, how HTTP protocol works, and how the sequence of messages are exchanged between our host and a server in order to transfer data from server to host and host to server. That concludes our today's lecture. Thank you. If there are any questions, please, I'll take your questions now.
सर आपने यूडीपी का बताया है कि वो स्पीड की वजह से और टाइमिंग की वजह से हम वो यूज़ करते हैं।
जी जी जी।
और सर पीछे स्लाइड में लिखा हुआ था कि यूडीपी डज नॉट प्रोवाइड टाइमिंग।
कहाँ पे लिखा है?
सर ये टीसीपी और यूसीपी जो था ना,
जी जी, मैं एक मिनट।
ट्रांसफर प्रोटोकॉल सर्विस।
Yeah, so that's a very good question. See, हमने कहा था कि जो TCP है वो रिलायबिलिटी देता है, मतलब कॉम्प्लेक्स, इसमें मैसेजेस आप भेजते हैं, आपके पास एक्नॉलेजमेंट आती हैं। टाइमिंग इन जनरल, टाइमिंग गारंटीज जो है ना, इन जनरल मैंने पहले भी बात की, मैं दोबारा कर देता हूँ। टाइमिंग and throughput guarantees in general are very hard to provide in networks. ये मैंने एक स्टेटमेंट बोली, मैं दोबारा कह देता हूँ, ठीक है? ओके, आई रिपीट, फिर मैं आपके सवाल की तरफ भी आता हूँ।